communication device constructed with electronic components. In today's session, let us see how to dismantle a given mobile phone and identify its major sections and parts. Smartphones should only be dismantled for refixing any physical issues in the phone, as mishandling may lead to unnecessary problems.
Objectives. At the end of this session, you will be able to dismantle the given cell phone or smartphone, identify the different sections and parts of the cell phone or smartphone, and reassemble the given cell phone or smartphone. First, let's look at the tools and equipment needed for dismantling and assembling the cell phone or smartphone. We will need the following: gloves, 1 pair; mobile phone, 1 number; screwdriver, 1 number; tweezers as required; spudger, 1 number; mobile phone opener, 1 number; universal liquid for frame, 1 number; LCD screen separator machine, 1 number; gum, 1 number; and SIM ejector, 1 number. Let's now see how to dismantle a smartphone or cell phone. Step 1. Prepare the phone. First, switch off the phone and disconnect any power source. Gather all the necessary tools and cleaning materials. Step 2. Remove the SIM card tray. Now locate the SIM card tray on the side of the phone. Insert the SIM card ejector tool into the small hole next to the tray. Apply gentle pressure to eject the tray. Remove the SIM card tray from the phone. Safety tip: be gentle to avoid damaging the tray or the phone's SIM card slot. Once removed, set the tray aside in a safe place to prevent it from getting lost. Step 3. Remove the back cover. First, heat the back panel using the separator machine for easily removing the back cover. Now rotate the phone and use a suitable tool to carefully lift and remove the back cover of the phone. Start from one corner and work your way around the perimeter of the phone until the cover loosens. Step 4. Remove shield cover of motherboard. Unscrew the screws securing the shield cover above the motherboard. Use an appropriate screwdriver to carefully remove these screws. Keep them in a safe place for reassembly later. Step 5. Remove shield cover of charge connector board. Locate and unscrew the screws securing the shield cover above the charge connector board. Now use the spudger to remove the shield cover. Safety tip: take care not to apply too much pressure as there may be fragile components underneath. Once removed, set the shield cover aside safely. Step 6. Remove the battery. To remove the battery, first remove the battery connector. Then apply a specialized liquid solution to dissolve the adhesive holding the battery in place. Carefully remove the battery once the adhesive has loosened using spudger. Step 7. Remove the motherboard. Locate and disconnect the strips connecting the CC board to the motherboard. Next, locate the display strip connector on the motherboard and carefully disconnect it. Next, locate the antenna cable connector on the motherboard and carefully disconnect it by using tweezer. Now remove the finger strip from the motherboard. With all connections detached, carefully lift the motherboard from its position within the phone. Step 8. Remove the charge connector board. First, remove the ringer set. Next, locate the antenna cable connector on the CC board and carefully disconnect it. Now identify any ribbon cables or strips connecting to the CC board and gently detach them. With all connections detached, gently lift the CC board from its slot within the phone. Step 9. Remove the components. Now remove the antenna cable from the phone, ensuring both its ends are detached. Next, identify the power on or off strip and volume strip components within the phone and carefully remove them. Locate the vibrator component within the phone and carefully remove it from its slot. Step 10. Remove the display. Now rotate the phone. Then after heating, apply a liquid solution to soften the adhesive securing the display. Carefully pry and lift the display from the phone chassis. Let's now start identifying the parts of the smartphone. Step 1. Prepare workspace. Set up a clean and organized workspace to lay out the dismantled parts of the mobile phone. Step 2. Locate motherboard. Find the main circuit board known as the motherboard among the dismantled parts. The motherboard is usually the largest component. Step 3. Find processor chip. Identify the dedicated processor chip mounted on the motherboard. This chip is responsible for executing instructions and performing calculations. Step 4. Spot RAM chip. Next to the processor, locate the RAM chip. This chip provides temporary data storage while the device is powered on. Step 5. Identify proximity sensor. Look for the proximity sensor positioned on the top part of the motherboard. This sensor detects nearby objects without physical contact. Step 6. Locate power IC. Find the power IC which manages power distribution and ensures proper functioning of the device. Step 7. Find network section. Identify the network section on the motherboard responsible for cellular connectivity components. Step 8. Spot flashlight. Locate the flashlight component on the motherboard responsible for providing illumination for the device's camera. Step 9. Remove cameras. Remove the front and back camera modules from the motherboard. These modules capture images and videos. Step 10. Find SIM tray. Identify the SIM tray slot on the motherboard where the SIM card is inserted for cellular communication. Step 11. Locate power and volume strip. Find the power and volume strip along the edge of the motherboard. These buttons control the device's power and volume settings. Step 12. Identify charge connector board. Locate the charge connector board usually at the bottom of the phone where the mic, USB port and headphone jack are located. Step 13. Spot vibrator. Finally, identify the vibrator component near the charge connector board responsible for producing vibration alerts for notifications and calls. Let's now see the assembling procedure. Step 1. Placing the display. First, carefully place the display onto the main body of the phone using gum. Ensure that the display is oriented correctly and aligns perfectly with the edges of the phone's main body. Safety tip. Take care to avoid pressing too hard on the display to prevent damage to the screen or the connectors underneath. Step 2. Attach power and volume strips. Now delicately position the power on or off strip and volume strip onto their designated slots on the phone's frame. Step 3. Attach front and back cameras to motherboard. Locate the connectors on the motherboard for the front and back cameras. Carefully reconnect each camera to its corresponding connector, ensuring that they are properly aligned and seated securely. Safety tip. Take care not to apply too much force to avoid damaging the connectors or the camera modules. Step 4. Fix the motherboard. Gently secure the motherboard into place within the phone's frame. Now attach the display strip to the motherboard. Step 5. Attach the vibrator. Secure the vibrator onto the CC board. Ensure it is properly aligned and firmly in place. Step 6. Place the CC board. Position the CC board into place and connect its cable securely to the motherboard. Step 7. Attach strips. Now attach the finger strip sensor to the motherboard and also place the antenna cable. Step 8. Fix the battery and connector. Slide the battery into its compartment and firmly connect the battery connector to the motherboard. Now place the ringer set onto its designated slot. Step 10. Position the shield cover. Now gently position the shield cover above the CC board and motherboard, ensuring proper alignment. Step 11. Secure the assembly with screws. Once everything is securely in place, carefully insert and tighten all screws to secure the components together. Step 12. Place back cover. For placing the back cover, first apply glue on the cover. Now carefully place the back cover onto the phone's frame. Step 13. Insert SIM card tray. Finally, insert the SIM card tray into its designated slot. Ensure it slides in smoothly and securely.
This brings us to the end of the session. In this session, we have learned to dismantle the given cell phone or smartphone, identify the different sections and parts of a cell phone or smartphone, reassemble the given cell phone or smartphone. Thank you for watching, and we will see you in the next session. Hello and welcome to the session. Today, we will discover how we change audio signals into FM signals and then back again using the OFC trainer kit. We will learn step by step how it is done, from tweaking the signal to understanding how it is decoded. Join us on this exciting journey through the world of sound and electronics.
Objectives. At the end of this session, you will be able to explain frequency modulation and demodulation, and demonstrate frequency modulation and demodulation using OFC trainer kit by audio signal. Modulation is the process of varying a carrier signal's properties such as amplitude, frequency, or phase in accordance with the information signal being transmitted. The carrier signal acts as a carrier for the information, allowing it to be transmitted efficiently through a medium such as air in the case of radio waves, or cables as in the case of wired communication. Need for modulation. Increase signal strength. The sender's baseband signals are not capable of direct transmission. The message signal strength should be increased so that it can travel longer distances. This is where modulation comes into play. Wireless communication system. Modulation eliminates the need for wires in communication systems. This is due to the fact that modulation is widely used in transmitting signals from one location to another at a faster rate. Size of the antenna. Signals in the 20 Hz to 20 kHz frequency range can only travel a short distance. The length of the antenna used to send the message signal should be 1/4 of the frequency used. As a result, modulation is required to raise the frequency of the message signal and increase its strength so that it can reach the receiver. Different types of modulation: amplitude modulation, frequency modulation, and phase modulation. Frequency modulation. The modulation where the frequency of the base signal changes by superimposing it with a carrier signal having a different frequency is frequency modulation. Let us look into each block of the optical fiber communication kit. Function generator. This block in the kit generates the signal at different frequencies and waveforms such as sine, square, etc. Frequency modulation, or VCO. This technique encodes information onto a carrier signal by varying its frequency that changes the frequency of the function generator's signal based on the data to be transmitted. Emitter circuits. These circuits take the electrical signal possibly modulated by the FM unit and convert it into a light signal. This light signal is then launched into the fiber optic cable. Detector circuits. When the light signal reaches the other end of the fiber optic cable, These circuits convert it back into an electrical signal. Comparator circuit. Comparator circuits generally compare two signals and output a high or low voltage depending on the comparison. Phase locked loop or PLL detector. This circuit helps recover the original data signal from the received electrical signal. Low pass filter. This filter removes high frequency noise from the recovered electrical signal, leaving behind the original data with minimal distortion. AC amplifier circuits. These circuits amplify the weak electrical signal received by the detector circuits, making it strong enough for further processing or analysis. Next, we will perform FM modulation and demodulation using OFC trainer kit using audio signal. For this, you will need the following tools and equipment such as optical fiber communication trainer kit 1 number, fiber optic cable 1 number, banana pins as required, CRO or cathode ray oscilloscope 1 number, and probe 2 numbers. Let's now dive into performing FM modulation and demodulation using OFC trainer kit by audio signal. Step 1. Power supply connection. To ensure proper operation, let's start by establishing the power connections for both the OFC trainer kit and the cathode ray oscilloscope or CRO. Begin by plugging in the power cords of both devices into their respective power outlets. Double-check that the power switches on both devices are in the on position before proceeding. Step 2. Set up signal generation. Now let's set up the signal generation. Using the built-in function generator of the OFC trainer kit, generate a sine wave signal with a frequency of 1 kHz. Connect the suitable wire to the function generator input. Adjust the frequency and amplitude settings on the function generator as required. Typically, the frequency and amplitude controls can be adjusted using knobs on the front panel of the function generator. Step 3. Connect to the oscilloscope or CRO. Take a probe and connect it to the channel 1. Now connect the output of the function generator to the selected input channel of the CRO. Use the red probe for connecting the input signal and connect the black probe to the common ground. Step 4. Verify signal characteristics. Now observe the waveform on the CRO screen. Use the following equations for verification. Amplitude A is equal to number of vertical divisions multiplied by volts per division. Now observe the vertical divisions and volts per division on the CRO and calculate the amplitude. Time period T is equal to number of horizontal divisions multiplied by time per division. Observe the number of horizontal divisions and time per divisions and record the time period. Now calculate the frequency by observing the time period. Frequency F is equal to 1 divided by time period or T. Step 5. Perform frequency modulation or FM. Now connect the function generator output to the input of the voltage-controlled oscillator of the frequency modulator block. Connect the signal output of the frequency modulator to the selected channel on the CRO. For this, use another probe and connect it to the channel 2. Connect the red probe to the output and black probe to the ground. Adjust the settings on the oscilloscope, such as the vertical and horizontal scales, to properly display the modulated signal waveform. Also adjust the time divisions and the volts or divisions of the respective channel. You should now be able to observe the modulated signal on the oscilloscope screen, which represents the frequency modulated output generated by the frequency modulator. Step 6. Prepare for transmission. Now connect the output of the frequency modulator to the input of the emitter circuit. Use a suitable cable to connect this output port to the input port of the emitter circuit. The emitter circuit likely has different operating modes, including analog and digital modes. For transmission through fiber optic cable, we need to set the emitter circuit to digital mode. The next step is to connect one end of the fiber optic cable to the emitter circuit's output terminal. Next, we will connect the other end of the fiber optic cable to the input of the detector circuit. Ensure the fiber optic cable is connected at both ends. Safety tip. It is crucial to handle fiber optic cables carefully to avoid damage to the fiber strands or connectors. Step 7. Demodulation setup. Connect the output of the detector circuit to the input of the comparator circuits. Ensure that this end of the cable is terminated with appropriate connectors compatible with the input port of the comparator. Next, we will connect the comparator's output to the input of the phase locked loop or PLL detector. Use suitable cables or connectors to establish this connection, ensuring that the signal path from the comparator to the PLL detector is properly connected. Step 8. Observe demodulated signal. Next, we will connect the output of the PLL detector to the input of the low-pass filter circuit. The low-pass filter circuit helps remove any high-frequency noise or interference present in the demodulated signal. Next, we need to amplify the filtered signal to achieve a suitable amplitude for observation. For this, connect the output of the low-pass filter circuit to the input of the amplifier circuit using appropriate cables or connectors. Connect the output of the AC amplifier to channel 2. Connect the red probe of the channel to the output of the AC amplifier circuit and the black probe to the common ground. Ensure that the signal path from the amplifier output to the oscilloscope input is properly routed and securely connected. Adjust the knobs of the comparator to see the signal correctly. Also adjust the time division knob to ensure that the waveform is displayed with the correct timing and resolution, making it easier to analyze its characteristics and features. Verify that the output signal taken from the amplifier circuit and the input signal are the same.
This brings us to the end of this session. In this session, we have learnt frequency modulation and demodulation and demonstration of frequency modulation and demodulation using OFC trainer kit by audio signal. Thank you for watching. We will see you in the next session. Hello and welcome to this session. Today, we are going to explore how we can use the OFC trainer kit to change our voices into radio signals and back again. It's like turning our words into invisible waves that travel through the air and then transforming them back into sound. Let's dive in and see how it all works.
Objectives. At the end of this session, you will be able to explain frequency modulation and demodulation and demonstrate the frequency modulation and demodulation using OFC trainer kit by voice link. Demodulation is defined as extracting the original information carrying signal from a modulated carrier wave. A demodulator is an electronic circuit that is mainly used to recover the information content from the modulated carrier wave. Need for demodulation. Demodulation is the process of recovering the original signal from the modulated signal. The modulation of the signal is done to transmit the signal over long distances by decreasing the bandwidth requirements. It also helps in multiplexing, which means that multiple signals can be transmitted over a single channel, resulting in efficient use of the spectrum. The modulation is done with the help of radio frequency which is outside the audible range of the human ear. To retrieve the original information and make it in the audible range for humans, the demodulation process is required. Different types of demodulation. They are amplitude demodulation, frequency demodulation, and phase demodulation. Frequency demodulation. Frequency demodulation, also known as FM demodulation, is the process of extracting the original information signal from a carrier wave that has been modulated in frequency. Types of frequency demodulation. They are slope detector, ratio detector, and phase locked loop or PLL. Slope detector. Slope detection is a simple method used for frequency demodulation. It relies on the fact that the frequency deviation in an FM signal corresponds to changes in the signal's slope. Operation. The FM signal is passed through a circuit that detects changes in its slope. The output of this circuit is proportional to the frequency deviation and thus the modulating signal can be recovered. Ratio detector. Ratio detection is a more sophisticated technique that compares the phase difference between the input FM signal and a local oscillator. Operation. The input FM signal is mixed with a local oscillator signal at the carrier frequency. The phase difference between these signals is then compared and the output is proportional to the frequency deviation. Phased locked loop or PLL. A phased locked loop is a widely used demodulation technique for FM signals. It locks onto the phase of the carrier wave and tracks its frequency variations. Operation. The incoming FM signal is compared with a voltage-controlled oscillator or VCO output. Advantages of demodulation. It helps in the efficient use of the bandwidth by allowing multiple signals to pass through a single channel. It helps recover the original signal, which is essential to retrieve the original information from it. It improves noise immunity, which helps in improving the reliability of the signal. It can demodulate the AM, FM, and PM signals. This helps in improving the diversification of demodulation and can be used in a wide range of applications. Applications of demodulation. Radar system. The demodulation technique is used in the radar system to extract information about range, angle, and many more. It helps in navigation, weather monitoring, and defense. Television. The demodulation technique is used to recover the video and audio signals, which helps in proper displaying of the television programs. Radio broadcasting. Demodulation is used to extract the audio signals which is to be broadcast. It can retrieve AM and FM signals to broadcast over a wide range of frequency spectra. Underwater communication. For underwater communication, acoustic signals are used. These signals need to be demodulated to receive the original information coming from the deep sea. Medical. The demodulation technique is used to generate the image of internal organs. It is widely used in MRI and ultrasound. Next, we will perform FM modulation and demodulation using OFC Trainer Kit by VoiceLink. For this, you will need the following tools and equipment such as Optical Fiber Communication or OFC Trainer Kit 1 number, Fiber Optic Cable 1 number, banana pins as required, mic 1 number. Now let's see the steps to perform FM modulation and demodulation using OFC Trainer Kit by VoiceLink. Power supply connection. To ensure proper operation, let's start by establishing the power connection for the OFC Trainer Kit. Begin by plugging in the power cords of the device into the power outlet. Double-check that the power switch is in the on position before proceeding. Connect the microphone. The first step is to connect the microphone to the audio input circuit of the OFC Trainer Kit. This will enable us to input the audio signal that we want to transmit through the optical fiber communication system. Ensure that the connections are securely made to prevent any signal loss or interference. Connect to frequency modulator. Next, let's prepare the voice link for modulation by connecting it to the frequency modulator. For this, locate the output port of the audio input circuit on the OFC trainer kit. Using a suitable cable, take the output signal from the audio input circuit and connect it to the input port of the frequency modulator. Prepare for transmission. Now connect the output of the frequency modulator to the input of the emitter circuit. Use a suitable cable to connect this output port to the input port of the emitter circuit. The emitter circuit likely has different operating modes, including analog and digital modes. For transmission through fiber optic cable, we need to set the emitter circuit to digital mode. The next step is to connect one end of the fiber optic cable to the emitter circuit's output terminal. Next, we will connect the other end of the fiber optic cable to the input of the detector circuit. Ensure the fiber optic cable is connected at both ends. Safety tip: it is crucial to handle fiber optic cables carefully to avoid damage to the fiber strands or connectors. Demodulation setup. Connect the output of the detector circuit to the input of the comparator circuits. Ensure that this end of the cable is terminated with appropriate connectors compatible with the input port of the comparator. Next, we will connect the comparator's output to the input of the phase locked loop or PLL detector. Use suitable cables or connectors to establish this connection, ensuring that the signal path from the comparator to the PLL detector is properly connected. Observe demodulated signal. Next, we will connect the output of the PLL detector to the input of the low-pass filter circuit. The low-pass filter circuit helps remove any high-frequency noise or interference present in the demodulated signal. Next, we need to amplify the filtered signal to achieve a suitable amplitude for observation. For this, connect the output of the low-pass filter circuit to the input of the amplifier circuit using appropriate cables or connectors. Retrieving the original signal. Now connect the output of the amplifier circuit to the input of the audio output circuit using suitable cable. Listen to the demodulated signal. To listen to the demodulated voice link, we have to connect the headphones to the output of the audio output circuit. Without headphones, we can directly hear the voice link from the audio output circuit block using the inbuilt speaker.
Fiber optic communication. Fiber optic communication. Okay.
This brings us to the end of this session. In this session, we have learned frequency modulation and demodulation, and demonstration of frequency modulation and demodulation using OFC trainer kit by Audio Signal. Thank you for watching. We will see you in the next session.
Hello everyone. In today's video, let us learn how to inspect solder joints, detect the defects and test the PCB for rework.
At the end of this video, you will be able to inspect the solder joint for any defects, detect the type of defect in the solder joint, test the given PCB for rework. Let us collect the tools and equipment required to do this practical. Trainees toolkit, magnifying lens, soldering iron set 25 watt 230 volt, safety goggles, IPA solution, cleaning brush, cleaning cloth, desoldering pump. Inspection of the soldered joints. Collect the defective PCB for the inspection. Make visual inspection on the board for any physical damage or defect. Identify the residuous flux area on the PCB. Clean the residuous flux on the solder joint using IPA solution with brush. Spray or flush the IPA solution on the brush, ensuring it is adequately saturated but not dripping. Be cautious not to use too much solution, as excessive moisture can lead to electrical shorts or damage to sensitive components. Gently scrub the solder joints and surrounding areas with a brush soaked in IPA solution. Focus on areas where flux residue is visible, applying light pressure to effectively remove the residue without damaging the solder joints or components. Using magnifying lens, carefully observe the shape of the joint formation, surface texture, mechanical bonding, and any brown wax-like material. Let us discuss the how to identify the various types of soldering joint defects that usually occur in the PCB. Dry joint or cracked joint. Look for signs of poor soldering such as incomplete solder coverage, irregular shape, or visible cracks in the solder using a magnifying lens. Dry joints or cracked joints may exhibit movement or flexing, indicating a lack of proper adhesion between the solder and the component lead or PCB pad. Dry joints or cracked joints may feel uneven or bumpy compared to properly soldered joints. Poor solder joint or lifted component. Look for irregularities such as insufficient solder, solder bridges, shorts between adjacent pads, solder balls, or solder spatter. Check if components are properly aligned with their respective pads. Misaligned components may indicate poor soldering or lifted leads. Look for components that appear raised or tilted on one side. This could indicate that the component is not fully soldered to the PCB or that one or more leads are lifted. Excess solder on joints. Look for signs of excessive solder such as solder blobs, solder bridges, shorts between adjacent pads, or solder spatter. Examine the shape and profile of the solder joints. Excess solder may form irregular shapes or bulges, particularly around through-hole components. Wetting defects. Look for signs of poor wettings such as incomplete coverage of solder on component leads or PCB pads. Examine the solder fillets formed at the junctions between component leads and PCB pads. A properly wetted joint should have a smooth, concave shaped solder fillet with good contact between the solder and the surface being joined. Blowholes. Look for signs of blowholes such as small cavities or bubbles within the solder. Check for irregularities in the solder surface such as dimples or depressions, which may indicate the presence of blowholes. Temperature defects or overheating. Carefully examine the PCB surface and components under good lighting. Look for signs of temperature-related damage such as discoloration, burn marks, or charred areas. Check for components that appear deformed, melted, or cracked, which may indicate exposure to excessive heat. Lumps of charred flakes. Charred flakes typically appears as irregularly shaped blackened lumps. They might have a rough or grainy texture due to the charring process. Flux is usually a mixture of various chemical compounds designed to aid in the soldering process, such as borates, silicates, and fluorides. When charred, these compounds might undergo changes in color and texture. Removal of through-hole component solder joint using desoldering pump. Take a defective board and identify the component to be removed. Start by visually inspecting the board for any obvious signs of damage or defects. Look for burnt components, cracked solder joints, bulging capacitors or any other abnormalities using a magnifying lens. Inspect the size of the solder joints on the component using magnifying lens. Carefully examine the size of the solder joints under magnification. Pay attention to their width and consistency. If the sizes of the solder joints are minimal, apply additional solder to form an excess solder joint. Turn on the soldering iron and allow it to reach its operating temperature. With the soldering iron heated and properly tinned, carefully apply additional solder to the existing joints. Touch the solder wire to the joint while simultaneously applying heat with the soldering iron tip. Allow the solder to flow and form a smooth, shiny joint. Identify the defective component that has to be removed from the PCB board. Use a soldering iron to heat the solder joints of the component you want to remove. Apply the tip of the soldering iron to the joint and allow it to heat the solder until it becomes molten. Hold the desoldering pump in one hand and position the nozzle of the pump over the molten solder joint. Ensure that the nozzle is directly above the joint and forms a good seal with the board. Press the plunger or trigger of the desoldering pump with your thumb to create a vacuum. This vacuum will suck up the molten solder into the pump's chamber, removing it from the joint. After engaging the desoldering pump, release the plunger or trigger to release the vacuum pressure. This will allow the solder to remain trapped inside the pump's chamber. Repeat the desoldering process until all solder is removed. After using the desoldering pump, inspect the solder joint to ensure that the solder has been completely removed and the component is free to be lifted from the board. Once the solder has been removed, carefully lift the component from the PCB board.
In this video, we have learned how to inspect the solder joint for any defects, detect the type of defect in the solder joint, test the given PCB for rework. This concludes the exercise. Thank you for watching. Hello everyone. In today's video, let us learn how to identify 2, 3, 4 terminal of SMD components. For ease of learning, the video is split into two parts. Part 1 will cover how to identify the 2 terminal SMD components, the resistor, capacitor, and find their values. The rest will be covered in part 2.
At the end of this video, you will be able to identify the 234 terminal of SMD components, decode the printed code letters and record the values of SMD components. Let us collect the tools and equipment required to do this practical. Trainees toolkit, LCR meter with props, magnifying lens, assorted 234 terminal SMD components, resistors, capacitors, transistors, ICs as required. Let us discuss SMD components. SMD components are much smaller than through-hole components, making them ideal for compact electronic devices where space is limited. Their small size also enables manufacturers to design sleeker and more lightweight products. SMD components are soldered directly onto the surface of the PCB using specialized soldering techniques such as reflow soldering or wave soldering. This eliminates the need for holes in the PCB, reducing manufacturing costs and simplifying the assembly process. There are various types of SMT components including resistors, capacitors, diodes, transistors, integrated circuits, and more. SMT components offer several advantages over through-hole components, including higher component density, better electrical performance, and improved thermal characteristics. Identification of two-terminal SMT devices. The major two-terminal components of SMT devices are resistors, capacitors, inductors, diodes, and LEDs. Let us discuss SMT resistors. Position the magnifying lens over the SMT resistor you want to identify. SMT resistors typically have a rectangular shape with metallic areas on the narrow ends of the chip which allows soldering. SMT resistors typically have markings consisting of 3 or 4 digits. In 3-digit SMT resistors, the first 2 digits represent the significant digits of the resistance value and the third digit, if present, represent the multiplier. The first 2 digits are 47, indicating the significant digits of the resistance value. The third digit 3 represent the multiplier. In this case, it stands for 10 to the power of 3 or 1000. So the resistance value would be 47 into 10 to the power of 3, which is 47,000 ohms or 47 kilo ohms. In 3-digit 222 resistor, the first 2 digits 22 represent the significant digits of the resistance value. The third digit 2 represent the multiplier. The multiplier is represented in powers of 10. In this case, 2 represents 10 to the power of 2 or 100. Combining the significant digits and the multiplier, the resistance value can be calculated as 22 into 100, which equals 2200 ohms or 2.2 kilo ohms. In 4-digit 4702 resistor, the first 3 digits are 470, indicating the significant digits. The fourth digit 2 represent the multiplier. In this case, it stands for 10 to the power of 2 or 100. So the resistance value would be 470 into 100 is 47,000 ohms or 47 kilo ohm. The SMT resistor notation 2 or 2 follows a slightly different convention compared to the standard 3 or 4 digit code. Numeric value. The 2R2 notations represents a resistor value of 2.2 ohms. RS decimal point. In the 2R2 notations, the letter R acts as a decimal point, so 2R2 translates to 2.2 ohms. Numeric value. The R56 notation typically represents a resistor value of 0.56 ohms. RS decimal point. In the R56 notation, the letter R acts as a decimal point, so R56 translates to 0.56 ohms. SMT capacitors. SMT capacitors have metallized connections at their both ends. SMT capacitors typically have a rectangular or square shape with rounded edges. Types of SMT capacitors. SMT ceramic capacitors, SMT tantalum capacitors, SMT electrolyte capacitors. SMT ceramic capacitors 10 microfarad 25 volts. Ceramic multilayer chip capacitors are available with a very wide range of values from 0.47 picofarad to 1 farad. In 0805 the length is 2 mm and width is 1.25 mm. In 1206 the length is 3.2 mm and width is 1.6 mm. The value of SMT ceramic capacitors is determined by the colors even if they don't have any markings. SMT capacitors are classified as Class 1, Class 2 and Class 3. Class 1 ceramic capacitors are typically white in color and have values that are lower than 1 to 10 picofarads. Class 2 ceramic capacitors are usually in light brown color. Their values range from nanofarad to microfarad and they are suitable for higher capacitance applications. Class 3 ceramic capacitors can be identified by their black or dark brown color as shown. This group of ceramic capacitor dielectrics provides lower capacitance at higher voltage compared to class 2 ceramic capacitors. Set the LCR meter in the capacitance mode in the appropriate range to measure the close value of the SMD ceramic capacitor based on its color. Measure the value of the SMD ceramic capacitor by placing LCR meter probes on both ends of the terminals. Tantalum capacitors are polarized components, meaning they have a specific orientation for correct operation. The polarized code at one side of the capacitor indicates positive terminal and the opposite side as negative terminal. SMD tantalum capacitors are typically constructed using a tantalum metal powder as the anode material, a tantalum pentoxide dielectric layer, and a conductive cathode layer. They are encapsulated in a molded epoxy or polymer casing, which provides protection and insulation. SMD tantalum capacitors are available in a wide range of capacitance values ranging from a few microfarads to hundreds of microfarads. The markings on SMD tantalum capacitors normally consist of 3 numbers. The first 2 form the significant figures and the third is the multiplier. Values are in picofarads. Therefore, the SMD tantalum capacitor shown has a value of 47 multiplied by 10 to the power of 5 picofarad, which works out to be 4.7 microfarad. SMD electrolyte capacitors typically consist of 2 aluminum foil electrodes separated by a layer of electrolyte soaked paper or polymer. SMD electrolyte capacitors are available in a wide range of capacitance values ranging from a few microfarads to several hundred or even thousands of microfarads. SMD electrolyte capacitors are polarized components, meaning they have a specific orientation for correct operation. The black mark serves as a visual indicator of the negative terminal of the capacitor. This ensures that the negative terminal is correctly connected to the negative pad on the PCB. Significantly, the opposite or other terminal is a positive one. Here, the capacitance value and operating voltage will be indicated at the top of the capacitor as shown.
In this video, we have discussed how to identify the 2-terminal SMD components, the resistor and the capacitor, and find their values. This concludes the part 1. See you in part 2. Hello everyone. In today's video, let us learn how to install and test the SMPS in PC.
At the end of this video, you will be able to install and test the SMPS unit in the given PC, power on the PC and check its working condition. Let us collect the tools and equipment required to do this practical. Trainees Toolkit, Digital Multimeter, Switched Mode Power Supply SMPS, PC with all peripherals. Let us discuss the importance of SMPS in the computer's CPU. Switched Mode Power Supply SMPS is a critical component in a computer's CPU. SMPS provides a regulated output voltage, ensuring stable power delivery to the computer's components. This stability is vital for preventing voltage fluctuations that could damage sensitive electronic circuits. SMPS is highly efficient compared to traditional linear power supplies. It converts AC power from the mains to low voltage DC power more efficiently, reducing energy waste and heat generation. This efficiency is crucial for maintaining stable power delivery to sensitive computer components. Install the tested SMPS unit in the PC. Remove or slide the side cover of the CPU. With the side panel removed, you are able to see the internal components of your computer like the motherboard, central processing unit, CPU, expansion cards, cooling fan, cables, and connectors. Identify the location of the SMPS in the CPU. The SMPS is typically at the top or bottom of the case at the rear. It is the metal box where the power card plugs into the computer. Take the tested SMPS and fix it like the input power socket of the SMPS comes on the rear side of the CPU. Carefully screw it in place, ensuring it is securely fastened but not over-tightened. Identify the main power connector. The main power connector from the SMPS to the motherboard is usually a large rectangular plug with many pins, 20 or 24 pins. It is typically located near the CPU socket on the motherboard. Align the main power connector from the SMPS with the corresponding socket on the motherboard. The connector should only fit in one orientation due to its shape and the arrangement of pins. Push the connector firmly into place until it is fully seated. SMPS will have additional cables for connecting power to other components such as drives, graphics cards, and case fans. These cables typically have connectors with specific shapes to match the ports on the devices they power. Connect the SATA power cable from the SMPS to any SATA drives, such as hard disk drives, HDDs, or solid state drives, SSDs. Match the connector from the cooling fan to the corresponding connector on the peripheral power cable from the SMPS. Ensure that the alignment is correct and that pins match up properly. Once all the cables are connected, use cable ties to organize and secure any loose cables inside the case. This helps improve airflow and prevents cables from interfering with other components. After ensuring all cables are properly connected and secured, close the CPU case by reattaching the side panels and tightening the screws. Checking the working condition of PC with power on. Ensure that the power switch on the back of the SMPS is in the off position before plugging in the power card. On the SMPS, you will find a power input socket, typically located on the rear panel of the unit. It's usually a standard 3-pronged socket. Take the power card that came with your computer or any standard computer power card. It should have a plug at one end and a 3-pronged connector at the other end. You may need to apply gentle pressure to ensure a secure connection. Take the other end of the power card and plug it into a standard power outlet. Ensure the power outlet is properly grounded and provides the appropriate voltage for your SMPS, usually a 230 volt 50 Hz AC supply. Switch on the power supply and power on the CPU by pressing power button in front panel. When you power on the computer, listen for the fans inside the case spinning up and any optical or hard drives powering on. These are indicators that the SMPS is supplying power to the components. If your computer is connected to a monitor, observe the display to see if it receives a signal from the graphics card or onboard graphics.
In this video, we have learned how to install and test the SMPS unit on the given PC. Power on the PC and check its working condition. This concludes the exercise. Thank you for watching.
In this continuing series of lecture on the reinforcement detailing of the various RC element in a structure, I will be covering the reinforcement detailing requirement of the RC slab in this particular presentation.